Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSE in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about graph algorithms. So for that, I'm going to discuss definition and terminologies. So the very first thing is that what is a regular graph? So what is a regular graph? So the graph in which the degree of all vertices should be same as is called as a regular graph. Okay, so the graph in which the degree of all vertices is same, then I can able to say that graph should be a regular graph. Suppose if all the vertices of the graph is of degree k, then it is called as k regular graph. Okay, if all the vertices in the graph is of degree k, then it is called as k regular graph. Suppose if I am going to have a graph like this, so what is the degree of a here? So that should be 1 and 2. So 2. What is the degree of B? So the two edges are incident on it. And here also same. So the degree of all the vertices is same in this graph. So it should be a regular graph. So it should be what we called as a 3 regular graph. So similarly, if I am going to have what is the degree of F2, E2, G2 and H2. So all should be the degree is same here for all the vertices, so that's why it should be a 4 regular graph. So a graph in which the degree of all vertices is same, then I can able to say that should be a regular graph. So based on the degree what I'm getting, so here the degree is all the vertices of degree, so that's why it should be a 2 regular graph. It is not be a 3 regular graph. And here also it should be a degree is 2, so it should be a 2 regular graph. So if all the vertices have degree 2, then I can able to say there are 2 regular graphs. And next one is that complete graph. So what is a complete graph? So a graph in which exactly one edge is present between every pair of vertices. So that's why we call it as a complete graph. So a complete graph of n vertices contains exactly NC2 edges. And a complete graph of n vertices is represented as Kn. So complete graph means a graph in which exactly one edge is present between every pair of vertices, then I can able to say that should be a complete graph. So I'm going to draw a graph like this. So these are the vertices. If I'm going to draw an edge for all the vertices from that vertex, I can able to say that should be complete. So from this vertex, I draw 3 edges to every other vertices. This is 1. If I consider 2, so I already one edge is present, and I'm going to draw another one, and I'm going to draw another one. So like this, I'm going to draw. And next one from 3, so already have an edge. And here also I'm edge. Here is not is having. So I'm going to draw this. So if I'm consider 4, so for already edges are present to all the remaining vertices, that should be 1, 2, 3. That's why it should be a complete graph. Okay, so a graph in which exactly one edge is present between every pair of vertices is a complete graph. So a complete graph of n vertices contains exactly NC2 edges. So a complete graph of n vertices is represented as Kn. Suppose number of vertices in this graph is 3, so that's why it should be a K3 graph. So the number of vertices is 4, that too it should be a complete graph. So that's why it should be K4. So here each vertex is connected with all the remaining vertices through exactly one edge. If I'm going to draw like this, if I'm going to draw another edge, so it may not be complete. So each and every vertex should be connected by only one edge only. And next one, what is a cyclic graph? So cyclic graph means a simple graph of n vertices where n should be greater than or equal to 3 and n edges going to form a cycle of length n is called as a cyclic graph. So in a cyclic graph, all the vertices are of degree 2 here. So this is the graph. So in which the degree is 2. So it should be a cyclic graph. So here also the vertices of the degree is 2. So it should be also a cyclic graph. Here also it should be a cyclic graph. So here each vertex is having degree 2. So both these are cyclic graph. So a simple graph of n vertices and n edges going to form a cycle of length n is called a cyclic graph. And in the cyclic graph, all the vertices of degree 2 here. So each vertex is going to have degree 2. So therefore, these are the cyclic graphs. So what is a cyclic graph? So a graph containing at least one cycle in it is called as a cyclic graph. So a graph in which it contains at least one cycle. So this here it is going to have one cycle and here also it is going to have another cycle. So if I'm going to draw like this, so this graph will also have one cycle. Okay, so that's why it should be a cyclic. So normally this graph is going to contain two cycles, therefore it should be a cyclic graph. And so whatever the graph you are drawing, so if I'm going to have one cycle, then it should be a cyclic graph. The next one, acyclic graph. So acyclic graph means a graph containing any cycle is what we call as a acyclic graph. So previously, so this edge is closed and this edge is closed. So I'm getting two cycles in this graph, so it should be a cyclic graph actually. So if these edges are not present, so there is no cycle exists in between them. So right, so that's why it should be a acyclic graph. So another example. So in this graph, no cycle is present. So that's why it should be a acyclic graph. Bipartite graph. So what is bipartite graph? So bipartite graph is a graph so where the vertices are going to be divided into two sets. So the vertex of set X only join with the vertex of another set. So the number of vertices belonging to the same set is known as bipartite graph. So if I'm going to have a set like this, A, B, C, D, E, so whenever I'm going to divide this as one under subset and this is under subset of vertices, and the mapping is done in between the two set of vertices, then I can able to say that should be a bipartite. So whenever the sets are going to be divided into two subsets and mapping is done between among those subsets, is called as bipartite. So ABCD is one set and PQ is another set. The mapping is done between these two. That's why it should be called as a bipartite graph. And next one is that planar graph. So what is a planar graph? So planar graph is the graph when I'm going to draw in a plane such that no two edges should not be cross each other. So whatever the graph I'm drawing on the plane, we should not cross with each other in such a way that we have to be construct the graph. So that graph is what we call as a planar graph. So some of the graphs will be looks like this. So it should not be a planar graph. It should not be a planar graph. It should not be a planar graph. So whenever the intersection of edges takes place in the graph, so that graph may not be treated as a planar graph. So this should be a planar graph. Why? Because no edges are going to be intersected here. Next one, pseudograph. So what is the pseudograph? So a graph having no parallel edges but having self loops is called a pseudograph. Okay. A graph having no parallel edges but having self loops in it is called as a pseudograph. So example of this pseudograph looks like this. So a graph containing no parallel edges but having the self loops. So I'm going to draw a graph. So if I'm going to have a graph like this, so having self loop and having multiple loops, multiple edges, then I can able this should not be a pseudo graph. So the graph which contains only self loops will be what we call as a pseudo graph. So here the graph consists of 3 vertices and 4 edges. So out of which the edge is a self loop here. So there are no parallel edges in this one. So but one self loop is present. That's why this graph should be called as a pseudo graph. And next one, simple graph. So simple graph means a graph containing no self loops and no parallel edges. Then I can able to say that should be a simple graph. So a graph having no self loops, no parallel edges is what we call as a simple graph. So the graph consists of 3 vertices and 3 edges. So there are neither self loops and not parallel edges. Therefore, it should be a simple graph. So a graph consists of 3 vertices and 3 edges, but it should not contain any self loops and parallel edges also, and that's why it should be called as a simple graph. So if I'm going to draw a graph, so it does not contain any self loops and then parallel edges as well. So that's why it should be called as a simple graph. The next one, what is the multi-graph here? So a graph having no self loops but having parallel edges is called a multi-graph. So a graph having no self loops but having parallel edges is called as a multi-graph. So example of multi-graph is this one. So whenever the graph having multiple edges like this, I can able to say that should be a multi-graph. So this should be a multi-graph, and this should be also a multi-graph. Suppose if I'm going to have a self loop, it may not be a multi-graph. So here the graph consists of 3 vertices and 4 edges. So out of which one edge is parallel edge. So that too, no self loops are present here. That's why it should be a multi-graph. Euler graph. So Euler graph is connected in which all the vertices are even degree. So Euler graph is a connected graph in which all vertices are even degree here. So if I'm going to consider what should be the degree here, 2. So here also 2, here also 2, here also 2, here also 2. So in this case, what is the degree of D here? It should be 3 here. So it may not be a Euler graph. So Euler graph is a connected graph in which all vertices are even degree. Okay. So Euler graph is a connected graph in which all vertices are even degree. So this is the connected graph. So connected graph means there should be a connection between each and every vertex in the graph, and all the degrees of those vertices are also even. So therefore it should be a Euler graph. And next one is Hamiltonian graph. So what is this Hamiltonian graph? So if there exists a closed walk in a connected graph, so that visits every vertex of the graph exactly once, so except starting vertex, without repeating the edges, then such graph is called as a Hamiltonian graph. Okay. So if there exists a closed walk in the connected graph, so that visits every vertex of the graph exactly once, so except the starting vertex. So without repeating the edges, then the graph is called as a Hamiltonian graph. So this should be a closed walk graph, so that visits each and every vertex exactly once, except the first vertex. Okay, without repeating, then the graph will be called as a Hamiltonian graph. So the path in this one is, so A. From A I'm going to reach B. So from B to C, C to D, D to E, and A to F. So I visited all the vertices in the graph exactly once. So it should be called as a Hamiltonian graph. So the graph contains the closed part and visit all the vertices exactly once. So on all the vertices are visited without repeating the edges, therefore it should be a Hamiltonian. So the following table is used to represent the different types of graphs. So a simple graph will study simple normal graph, simple graph, multigraph, and pseudo. So if I'm going to consider a column like self loops, so the self loop may present only in graphs and then pseudograph only. And if I'm going to consider parallel edges, so the parallel edges means the edges are going to present only normal graph and then multigraph. Okay, so a simple graph may be to contain self loops and parallel edges. Normal graph. Simple graph means no self loops and no parallel edges. Multigraph means no self loops but having multiple edges. And pseudograph means self loop is present, no parallel edges. The next question, what is the BFS algorithm? So BFS means that breadth first search. So what is it? Breadth first search. So breadth first search is the traversal technique of the graph that visits all the vertices exactly once. So the BFS travel going to produce a minimum spanning tree as the final result. So the spanning tree is nothing but a graph without any loops here. And for implementing this BFS, we are going to use Q data structure with maximum of total number of vertices in the graph. Okay, to implement the BFS traversal. So BFS is a graph traversal technique and it is going to be used Q data structure. So the output should be spanning tree. Okay. So let us consider example how I'm going to construct this. So for that I'm going to have one more question. What is the BFS algorithm here? So BFS algorithm means, so first you have to define the Q of size of total number of vertices in the graph, and you have to be select any vertex as the starting point of the traversal, and then you have to visit the vertex and insert into the queue. So visit all the non-visited adjacent vertices, so which is at the front of the queue, and insert them into the queue. So whenever there is no new vertex to visit from the vertex, so it should be the front of the queue, then delete that vertex. So repeat the steps 3 and 4 until the queue becomes empty. And when the queue becomes empty, then it is going to produce this final spanning tree by removing unused edges from the graph. So define a queue of size of total number of vertices in the graph and select any vertex as the starting point of the traversal and visit that vertex and visit the non-visited adjacent vertices. So whenever there are no vertex to be visited from the vertex, and repeat the steps 3 and 4 until the queue becomes empty. So when the queue becomes empty, produce this final spanning tree. And we're going to construct this BFS is that, so if I'm going to have a simple graph like this, So I have to use queue data structure. So what is the initial point is this one. That one is going to be push on the insert into the queue. So next one, what are the adjacent vertices? B. So B is that. So that one has to be deleted. So for B, what is adjacent vertices? C and D. That one we push on to delete. And from C, already D is there. So C and that. So like this, we are going to construct the BFS order of this tree. So next, another one is that depth first search. What is depth first search? So it is also a bit traversal technique for the graph, which is going to produce the spanning tree as the final result. And this spanning tree is the graph without loops, and we're going to use the queue data structure with maximum number of total number of vertices in the graph to implement DFS traversal. So DFS travels of the graph produce the spanning tree as a final result, and here also the output should be same, but we are going to use queue data structure. So DFS stands for depth first search, and I'm going to use tag data structure here. And the output should be spanning tree. Okay, so what is the algorithm for this? So here we're going to be define first the stack size, the number of vertices in the graph, and select any vertex as the starting point of the traversal, and then visit that vertex and push it onto the stack. So visit any number of non-adjacent vertices of vertex which is at the top and then push it onto the stack. So visit any one of the non-adjacent vertices which is at the top of the stack and push it onto the stack. So repeat steps 3 until there is no new vertex to be visited from the vertex which is at the top of the stack. So whenever there is no new vertex to be visited, then use backtracking and prove the contents of the stack. And we have to repeat all the steps until the stack becomes empty. And when the stack becomes empty, then it is going to produce final spanning tree by removing unused edges from the graph. So for implementing this DFS, so we have to first name the stack size, and then have to randomly select any one vertex of the graph, and then we have to be visit non-adjacent vertices, and we have to be repeat the step until no new vertex is to be found, and we have to be repeat this. So whenever no new vertex is found, then have to again backtracking is going to be applied. So let us consider an example how we're going to construct the DFS. So DFS means, so this is the graph we're having initially. So first I have to visit this, and what is the next vertex? This one. So from this I'm going to visit this one, and from this I'm going to visit this one. So again I have to apply backtracking, and again apply this, and again I have to apply backtracking and do this. When it comes to BFS, so how it would be means. So first I have to visit this, and next I have to visit this one, and this one, level. And from here, again I have to visit the next level visiting, breadth-wise searching. Depth-wise means, so I have to visit level by level. So if it is whatever text is found, again I have to go back, and then again I have to perform under DFS order. So let us take an example. So A, B, C, D, E, F. So this is the graph. So DFS order I want to find. So first one is A. So push onto the stack. So what are the contents of the elements of this way? So that should be B, C, and then D. So push on the stack from the element of the stack. So next one is B. So what are the elements of B? E. So E. So there will be from the stack. And from B, E. So E is already there. So what are the elements of E? F is going to be from here it should be D. Should be the letter. And for D, I have to pop the D here. And then C. C and then D also are connected to both. So what is the minimum spanning tree? So spanning tree for the connected graph is the tree. So whose vertex should be same as the vertex set of the given graph, and whose edge set should be subset of edge set of the given graph. So the weight of spanning tree should be nothing but the sum of all the weights of edges in the tree. And minimum spanning tree is the spanning tree with the smallest possible weight. So if I'm going to get one span, this is the graph here. So if I'm going to get a spanning tree, so the weight minimum spanning tree weight means the sum of all the weights. So 1 plus 2 plus 3. That should be the minimum weight spanning tree. So spanning tree is the connected graph in which the vertex should be same as the vertex of the given graph. But weight of the spanning tree is nothing but the sum of the weights of all the edges of the tree. And minimum weight of the spanning tree is the minimum value we have to find out. So see the example. So if I'm going to have a graph like this, the possible spanning tree will be this. So if I'm going to have weights in the graph, so we're going to find the spanning tree minimum. So that should be the sum of the weight should be minimum. So 1 plus 2 plus 3. So what are the algorithms for the minimum spanning tree? So the minimum spanning tree can be constructed in two ways. So for that I'm going to have Driscoll's algorithm and Prim's algorithm. So the both algorithms are going to be different one. So mainly this Driscoll's algorithm is going to be used the edges, whereas the Prim's algorithm is going to be used the vertices connection. So in Prim's algorithm, at any instance of output, it represents the tree, whereas in Driscoll's algorithm, at any instance of output, it may be represented output, it may represent a tree or not. Okay, so in Prim's algorithm, at any instance of output, it represents the tree, whereas in Driscoll's algorithm, at any instance of output, it may represent a tree or not. So the algorithms that are available for construction of minimum spanning tree is that Driscoll's and then Prim's algorithm. So what is a Driscoll's algorithm? So Driscoll's algorithm is nothing but a greedy algorithm, and this greedy algorithm is going to show some local optimum, chooses some local optimum, that is picking an edge that should be the least weight. And the working of this Driscoll's algorithm is that, so take a graph with n vertices and then keep on adding the least cost edge, so while avoiding the creation of cycles until n minus m edges have been added. So sometimes two or more edges may going to have the same cost, but the order in which the edges are chosen, so that doesn't matter. So the different MSTs may result, but they're going to have the same total cost, which all will be the minimum cost. So Driscoll's algorithm is greedy algorithm. So initially I have to construct a graph. So in this graph, I'm going to construct minimum cost edges first, and then we have to keep on adding the smallest edge. So, but while adding is, it should not form a cycle. So, what is the minimum edge among this? So, this one is going to be added. What is the next minimum? So, I'm going to add. What is the next minimum? I'm going to add. What is the next minimum? 3. If I'm going to add, it is going to form a cycle. So, it should not be occur. So, next minimum 3. It should also be going to form a cycle. 4. It is also going to form a cycle. So, the minimum spanning tree is that. So, minimum cost is also 5. Okay. So, the Driscoll's algorithm is nothing but the greedy algorithm. So, it is going to be choose the local optimum value by that means picking an edge that is least weight, and the working is that, so take a graph of vertices and then keep on adding the shortest edge, and while avoiding the cycles, we have to be C, and then we have to add until and one service are going to be formed. So let us consider a graph first again. So this is the graph. So initially I have to consider the set of vertices, and what is the worst minimum I have to consider. So I'm going to take this one, and next minimum weight edge is that this one. Okay, I'm added, and next minimum I'm going to consider 2. So 2 added, and next one also 2, 3 also 2, and I'm going to consider this 3. So it is going to form the cycle. So that's why it should not be added. So I'm going to add this one. It must be added. I'm going to take this one. So cycle is formed. So it should not be considered. So 4 it may not be considered. And this would be the resultant minimum spanning tree. So the sum is that, so 1 plus 2 plus 2 plus 2 plus 8. So what is algorithm? Driscoll's algorithm. So make a tree as empty, repeat the steps 3, 4, 5, and then choose an edge and delete the edge from this edge, from the edge set E. So if the edge does not form a cycle, add it, otherwise it will be discarded. So how to repeat this process until the tree contains n minus 1 edges. Okay. So make a tree empty first and then repeat the steps 3, 4, 5. So until it is going to contain n minus 1 edges. So what is the first step? You have to be choose the edge that should be least one. You have to be considered, and then how to delete the edge from the edge set V. And if that edge does not create a cycle, then add it, and we have it display. And next one is the Prim's algorithm. So Prim's algorithm is also a famous greedy algorithm. So mainly it is going to be used to find the minimum spanning tree of the given graph. So to apply the Prim's algorithm, the given graph must be weighted, connected, and undirected. So in the spanning tree, so any vertex not in the tree but connected, so it may an edge that may be added. So this simple modified algorithm of the spanning tree is called Prim's algorithm. So the Prim's algorithm is famously algorithm is going to be used to find the spanning tree, and how to apply this algorithm to the minimum graph that should be weighted connected. So in the spanning tree algorithm, so any vertex not in the tree but connected to an edge can be added. So the simple and modified spanning tree is here. Prim's algorithm finding the minimum for spanning tree. Right. So consider a graph here. So in this Prim's algorithm, first you have to be consider the minimum. Start from here. So according to Driscoll's means, how it will be? So this one, this one, this one, this one. So it is going to form the cycle. So this should be the resultant spanning tree according to Driscoll's. So according to Prince, first we have to choose one, and from also next one I'm going to choose from here, and next one is one I'm going to use. And from here, 3 is going to be next. So 3 is going to form the cycle, leave it. So next one is 2. So I'm going to construct. Next one is 3. So but I'm going to form the cycle. So that's why the resultant spanning tree should be same. So according to critical sentence, the spanning tree should be same only, and cost is also same. Okay. So the Prim's algorithm is a famous Gray algorithm, and this is also same. Both are going to be used for finding the minimum spanning tree. So here, the Driscoll's algorithm have to be picking up the minimum edges and then add it onto the tree. Whereas in Prim's algorithm, we are going to be choosing the minimum edge from that vertex, and again from that vertex, we have to find it out. So let us consider another example like this, so that we can able to get the clear answer. So this is the graph given. So how to construct according to Prim's algorithm. So I'm going to start from 1. So here, what is the minimum weight? That should be 2. That should be selected from here. Next minimum 8 is 9. 12, 2 is there. So I'm going to select 9. Now next from here, I'm going to select 4. From 4, I'm going to select 8 once it is not possible. To 5. So this should be the minimum spanning tree according to Prim's algorithm, and that 2 weight should be 2 plus 9 plus 4. Spanning the tree. So that should be 50. So like this, I'm going to construct the Prim's algorithm. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.